So the second presenter is Dr. Nali from University of Connecticut, and she will introduce her research in particle drifting phenomena. Dr. Lee is an assistant professor in the Department of Pharmaceutical Sciences at the University of Connecticut. She received her bachelor degrees in food science and engineering from South China University of Technology and PhD degree in food chemistry at Purdue University, followed by postdoctoral training in industrial and physical pharmacy at Purdue as well. Prior to joining UConn, she also worked at Crystal Pharmatech, specializing in solid-state chemistry and crystal form selection of small molecule drugs. Lab group, started in 2019 at UConn, focuses on understanding the physical chemistry underlying interactions between formulations and the in vivo environment. So I'm happy to see that we have no technical issues and everything is up and running. So Dr. Lee, please start your presentation.
Oh, thank you, Glenn, for the kind introduction. Everyone can see my slide and can hear me, right?
Yes.
Great, thank you. Thanks, Dr. Sugano, for the great introduction about the particle drifting effect. And building on his work, actually, my lab at UConn has done some experimental work to look into what are the key factors affecting the particle drifting effect. And therefore, today, I'm going to talk a little bit about the experiments we've done regarding the particle drifting effect as a function of drug selection and colloidal particle properties. Okay. So I think to this audience, I probably don't need to emphasize the importance of solubility because we all learned that only the solubilized drug can be absorbed, whereas insolubility of most drugs in the pipeline and on the market has posed a very significant problem to the pharmaceutical industry. And therefore, as a formulation scientist, we have been striving to develop a lot of formulation strategies to enable them to be absorbed, right? Because without these formulation strategies, then eating those life-saving drugs will actually be no different from eating a piece of brick. We'll get no absorption, no health benefit, no whatsoever. But even with the help of these solubility enhancement strategies, actually, there's only so much we can get in solution. So we have the drug dissolved here, showing in red molecules here, we only have so much. The rest, they either exist in, for example, undissolved crystalline particle form or nanocrystals, or amorphous aggregates that precipitate out from the solution because we have reached the miscibility gap and they form a cloudy solution, which I'm going to talk about later. Or they are bound with biomicelles or surfactant micelles. But in other words, they're not the free drug. But now, we do know that all these unfree form, particle form drug do get absorbed. They actually promote bioavailability to a great extent. And that's what's termed as the particle drifting effect. And therefore, today we're going to talk about, okay, how much does permeability get enhanced by the presence of these particles? And in our work, we used amorphous particles as a model system because they are easy to manipulate and we can easily change their properties. So before I delve into that, I want to briefly introduce the phase behavior of amorphous particles. So let's think of a commonly encountered example in daily life. Let's say we dissolve some table sugar in solution, then we get an unsaturated sugar solution, which is sweet, right? But if we keep adding that table sugar, then eventually we'll hit a point where we cannot dissolve it anymore. So there's going to be an equilibrium between the undissolved sugar and the sweet solution. We get a saturated sugar solution. However, by using a formulation strategy, let's make the table sugar into a cotton candy form, then we will be able to dissolve the cotton candy into that already saturated sucrose solution. We end up in a supersaturated region. This is because the cotton candy is the amorphous form of table sugar. So that's also how we utilize the amorphous formulation strategy to most of our drugs to achieve solubility enhancement. However, there's a question. So solubility enhancement strategy is so good, but can we dissolve infinite amount of solute in solution? Well, for poorly soluble drugs, then of course not. There is an upper limit of solution concentration. Here we termed it as amorphous solubility, but it's actually the miscibility gap between the drug and water. And therefore, even if we are able to dissolve more drug into the solution, that excess amount of drug above amorphous solubility will spontaneously precipitate out from solution and separate into a different phase in the form of monodispersed nanoparticles, so shown as here as a cloudy solution. So this is how we made our amorphous nanoparticles, and you often see them being generated during the dissolution of amorphous solid dispersions, or during the pH transit of a salt form, or during the digestion of a lipid-based formulation. Previously, they were termed under the umbrella term of precipitation together with crystallization. However, amorphous particles are so different from crystalline particles in terms of absorption outcomes, and therefore it's important that we need to differentiate them. Right. So based on Dr. Sugano's talk that we already know, particle form do contribute to absorption, right? So here I have another example showing exclusively enhanced absorption by the amorphous nanoparticles generated from amorphous formulations. This is animal data published by Merck using a poorly soluble drug called anacetrapib. And the very bottom line here that shows virtually no absorption, as you see, it's actually the control formulation, which is amorphous. They made it into a micronized particle form of 8 micron in diameter, and this drug is not expected to crystallize. So this is amorphous, however, it does not increase bioavailability. But if they formulate the API in the form of a fast-releasing amorphous solid dispersion that is able to release the drug quickly and beyond amorphous solubility and generate these amorphous nanoparticles, then you would see, okay, the bioavailability and drug absorption start to increase. And more interestingly is that the smaller the particles, the higher the absorption. So this does prove that amorphous particles are very, very important in vivo, and the smaller particles behave better, right? And the reason, as Professor Sugano already talked about, is because the major barrier for absorption is actually the unstilled water layer for poorly soluble drugs. So imagine the drug absorption process as a hiking journey, and we have to cross the unstilled water layer to get absorbed. And for now, only 2 of them has made it in the unstilled water layer, despite there's a huge population in the bulk. But if there are colloidal particles, let's say drug nanoparticles or biomicelles, then these particles could act as vehicles and carry a lot of free drug into the unstilled water layer. They can drop us off right at the surface of the intestinal wall such that we will be able to reach the destiny a lot quicker and in a lot more number. So this is how particle drifting effect works, but the next important question is, okay, how can we predict it with some accuracy, right? This is what everyone cares about. So I have to apologize that I have to show equations on a Tuesday morning, but I promise that these equations are very easy and very important for us to understand the particle drifting effect. So let's start from the very simple, easy, fixed law of diffusion, classic. We know the flux of the drug, which is the mass flow of a drug per unit time, per unit area. And it's defined as the permeability coefficient multiplied by the effective concentration of that solute, right? And then the permeability coefficient could be written as a function of the diffusion coefficient of the solute, as well as the thickness of the barrier, which is the unstilled water layer here. So we call it HUWL. And the concentration we can easily measure from the solution. So if we want to calculate the amount of drug absorption from the GI tract, then we just need to do integration of this equation to the surface area of the GI tract, as well as the time of drug transit in the GI tract. But now the question becomes, okay, but we have multiple species in addition to the free drug only, right? So how can we modify this equation to predict the particle drifting effect? I think one way of doing that, and a couple of papers in the literature have reported in a few attempts, is that we separate these solutions into different populations. So now we have a free drug portion and a particle portion. And then we write fixed law of diffusion into each species. So we got the free drug permeability coefficient, that's a function of the diffusion coefficient, and undisturbed water layer thickness. We also have the contribution from particles here with the undisturbed water layer thickness specific to the particles. And if we have multiple types of particles in the solution, let's say micelles and particles, then we can write another term, particle 2, particle 3, on top of this equation. But the simple thing is, look, the diffusion coefficient is a constant, concentration is a constant that we can measure from the solution, and the only thing we need to figure out is the undisturbed water layer thickness here. And then we can plug in the equation and do our calculation. And you know, the amount of drug absorbed is inversely proportional to the undisturbed water layer thickness, right? Because the thicker the barrier, then the harder for the solute to cross through, so we get lower absorption. Now, with that in mind, we started measuring the effective undisturbed water layer thickness. The experimental setup we used is a biphasic diffusion setup, where we have the aqueous phase here. We put our drug and the particles in the aqueous phase, and when we measure the drug in the organic phase, the appearance as a function of time. So this is an example showing drug concentration as a function of time in the organic phase. And you can see it increases exponentially until it reaches a plateau. That plateau value is pretty much how much drug we have put in the aqueous phase, whereas the time it takes to reach the plateau, it could be slow, could be fast. Then that's determined by the diffusional resistance, determined by the effective undisturbed water layer thickness at the interface. And therefore, we've written the differential equation and we solved it. We got an expression for our undisturbed water layer thickness. So basically, based on this concentration profile, we are able to extrapolate that effective undisturbed water layer thickness. So we started measuring the free drug. Here, we have a homogeneous molecularly dissolved drug. We picked poorly soluble drugs with different molecular weight, ranging from 200 to about 800. So that covered already most of the poorly soluble drugs already. And because molecular weight affects the diffusion coefficient of the drug, so we're trying to determine, okay, can we see a difference in the undisturbed water layer thickness or the mass transport rate across different drugs? But as you can see here, we do not. It appears to be quite similar, and the error bars are huge. So it seems like for most of the drug we are investigating, we could probably treat the undisturbed water layer thickness for the free drug as a constant. So that means experimentally determined undisturbed water layer thickness from one drug could be applied generally to many other drugs. That shouldn't cause a big issue in terms of prediction, which is pretty good. But in terms of amorphous nanoparticles, then things are not that simple. Similarly, we generated amorphous nanoparticles of 300 nanometer using a wide range of poorly soluble drugs, right? But here, as you can see, the diffusional profile of our drugs turn out to be very, very different. Some of them are really quickly, reaches equilibrium within about 3 hours, but some others take like days to reach equilibrium. So that really means the amorphous particles have some variability here. And if we further analyze that data, we plotted the 1 over HUWL. So let me remind you the equation we talked about again. Permeability coefficient is inversely proportional to HUWL, and therefore what we plotted on the y-axis is actually the effective permeability coefficient, or you can understand it as the drug absorbed in that organic phase. Whereas on the x-axis, we have the solubility of the drug then composing the particle, and we got a very, very nice linear correlation here. So if we recall that Whitney-Noyes equation, then we all know that dissolution rate of a particle is proportional to the solubility of the drug that makes up the particle. And therefore, it seems the particle drifting effect is closely related to the dissolution rate of the particle. The particle has to dissolve first, dump the drug at the membrane surface, and then the free drug can get absorbed. And of course, for some of the higher solubility drugs, such as tilaprevir then dissolution occurs really quickly, and we get a higher extent of particle drifting effect. Whereas for some other extremely insoluble drugs, such as anacetrapib, dissolution is so slow, and therefore we only get this much of permeability enhancement at the same particle size and same particle concentration. Next, we looked into the impact of particle size. Here I'm showing the data of two drugs, one called atazanavir, the other one called anacetrapib. So we made particles with different sizes, but you do not see any difference in the case of atazanavir, whereas for anacetrapib, we do see for smaller particles, then we do see the permeation curve is a lot faster compared to that from a larger particle. This kind of makes sense because if you think about particle dissolution, then smaller particles are expected to dissolve faster, whereas the larger particles are expected to dissolve slower. So this is within our expectation. But what about atazanavir? There's no difference, although we tried to manipulate particle size, right? Let's go back to the drawing board and think about the mechanism of particle drifting effect again. We just talked about, okay, the particles acting as vehicles, bringing a lot of drug to the unstirred water layer. However, it has to undergo dissolution first. And then the dissolved free drug permeates through membrane, so there is a permeation step. It's actually a sequential reaction between dissolution and permeation. And for the particular insoluble drug, anacetrapib here, dissolution is so slow such that it determined the rate of the overall reaction, and that's why if we tune the dissolution rate of the particle, we are tuning the overall reaction rate of this entire particle drifting effect. Whereas on the other hand, for the slightly more soluble drug, atazanavir, this drug has a higher solubility and hence higher dissolution rate. In this case, the second step, permeation, becomes the rate limiting step. So although we're still trying to change particle size, however, the rate limiting step is permeation, so that the entire particle drifting effect do not get altered by the changes in particle size. Next, we looked into the impact of particle concentration. And again, as a reminder, the permeability coefficient, or the particle drifting effect, is inversely proportional to the unstirred water layer thickness. And here I'm showing data for 3 drugs. As you can see, the unstirred water layer thickness increases as a function of particle concentration. So that really means, although we're getting more particles and the higher permeability enhancement, however, the normalized enhancement per concentration is actually decreased. So we're facing a slowed down permeation at higher particle concentration. Why did that happen? So let's look at the Whitney-Noyes equation again. We've already talked about the solubility factor, but there is also a bulk concentration factor, right? So here the bulk concentration is considered as the average concentration in that hypothetical unstirred water layer. And therefore, for dissolution to occur, then the maximum dissolution rate will only be determined when the bulk concentration is minimal. However, when we have a lot more particles, then we're actually increasing that bulk concentration within the unstirred water layer, and therefore we are facing a non-sink dissolution. That non-sink dissolution will slow down gradually with increasing particle concentration, and that's exactly what we are observing here. That's about drug nanoparticles, but another important type of colloidal drug particles is biomicelles, because those are endogenous surfactant existing in our GI tract. They're also important in terms of the food effect we often observe in poorly soluble drugs. So we picked sodium taurocolate, a representative bile, as a model system and made our bile salts. Here, the blue shows the free drug, which you have already looked at. They look similar across different drugs. We also measured the yellow, which is the free drug, in the presence of a low concentration of bile salt. This is below CMC, so we don't see any solubilization. But the only thing is that in a biphasic experimental setup, then excipients are known to slow down diffusion, when we do see that here happening for philodipine. So slowed down diffusion correspond to a thicker unstirred water layer thickness. But it didn't alter the unstirred water layer for the other 3 drugs. And then we measured the unstirred water layer thickness with respect to the micelle, which is shown in orange here. As you can see, for most of the drugs, danazol, efavirenz, and estradiol, and phenolipine, actually, the orange appears to be either similar, so as good as the free drug, or thinner, so that means that micelle-bound drug is even better compared to the free drug, as you see in the reduction in the unstirred water layer thickness. So that explains why food effect is so significant, especially for poorly soluble drugs, right? Because biomicelles act, if not similar, then even better than the free drug. We next also looked into the impact of micelle concentration. So if you recall a few slides back, we showed the impact of particle concentration, which shows an increase in unstirred water layer thickness as a function of particle concentration. But biomicelles shows the contrary. So we do see a decrease in unstirred water layer thickness as a function of biomicelle concentration. And if we look at the mechanism again, instead of having a particle here, we have a biomicelle that moves in the unstirred water layer and then undergoes dissociation, releases the free drug and the free micelle. But both the free drug and the free micelle can permeate through, so the free micelle actually gets absorbed really, really quickly, and that moves the equilibrium to the release side of things, causing a lot more release of the free drug in the unstirred water layer. And that's probably why at a higher biomicelle concentration, we're actually looking at an enhanced particle drifting effect. So I think, I hope by the end of the presentation, I've already convinced you that the particle drifting effect is indeed very significant. However, it's a highly dynamic process. It's a function of the type of colloidal particles we're looking at, and also is closely related to the specific process, the specific property of the drug. And therefore, we cannot really simply use a unified unstirred water layer thickness to predict everything. Instead, the best approach is probably to build a mechanistic mass transfer model and incorporate that impact of colloidal properties or drug properties in the equation such that we get a custom prediction for everything. And it's a sequential reaction between dissolution, dissociation of the micelle, and permeation. And therefore, either side of the reaction could be rate limiting. It really depends on the property of the drug. And last but not least, I want to thank my lab group at the University of Connecticut and all the funding agencies who supported these studies. And particularly Dahe Yang, graduate student, produced most of the data I'm showing here. And with that, I thank you again for your time and welcome any questions you might have.
Thank you very much now for this great presentation. And we have the first question, which is for Atazanavir. If permeation is indeed limiting because dissolution is fast, shouldn't smaller particles indeed impact flux absorption based on the PD theory?
So smaller particles do affect flux. I think the argument we're trying to make here is smaller particles behave as good as the larger particles in this specific case. I hope that answered the question.
Okay. Yeah, thank you. Another question. Drift of particles into in vivo mucous water layer is mediated by pore size in the latter as noted by Keo, while a simple unstable water layer in vitro linked to stirring rate has no such limitation. So can someone comment on the relationship between particle drift in vitro without mucous pores versus in vivo? I'm thinking about in vitro, in vivo extrapolation here.
Yeah, thanks for that question. This is actually $1 million question. Really, in vitro in vivo correlation is the difficult step here because things are so different, and my group as well as Q and the other groups around the world are all working in this area. We are currently working to have some in vivo data, but we don't have so much of a progress to have a definite answer to tell you what's correct or what's not. What I can say is this is in this in vitro setting, then we should use the mechanistic model to predict it. But in vivo, there are maybe much more involved. But the difficulty with in vivo, there's also a lot of confounding factor interfere with drug absorbance. So that gets complicated.
Thank you. Another question. What intrinsic property of atazanavir could be responsible for its permeability being the rate-limiting step despite particle size change?
Yeah, good question. So this is really because alazanavir is one of the higher solubility drug among all the poorly soluble drugs we've investigated. It's just so soluble, and the amorphous particles, they replenish the drug so well, so fast, and that made the permeability being the rate limiting step.
You mean permeability through the epithelial layer or the membrane itself? Yeah.
Yeah, but it's still a BCS class 2 or class 4 drug. Gets absorbed really quickly. It does not mean it's permeability limited absorption, but in this specific case, it's just because the solution is even faster.
Okay, thank you. One more question. Thank you for the nice presentation. Is there any study on the effect of unstable layer viscosity towards particle drift effect or vice versa?
Yeah, very good question. I think we will need more in vivo data, and maybe Kyo is already working on the clinical side. We will need to generate more in vivo data and to summarize more in vivo data to be able to reach the conclusion.
Thank you. One last question, as we're running out of time. How do we determine which of solubility in the unstable layer or the permeability will be responsible for the rate limiting step of the absorption of a drug?
I think this is also a in vivo kind of question. So in vitro, we can use a lot of experimental setup, and each will be different, but we will be only talking about the permeability limit with respect to that specific experimental setup. So the only meaningful answer will be in vivo data.
Okay, thank you very much. I think for the last minute, I think that's all the time we had. So thank you for all the participants for being a great audience and asking a lot of questions, and our speakers for their presentations. And thank you again for joining, and make sure you join us tomorrow as well, when we have two more exciting presentations on the same topic. One from Dr. Patrick Shinko, researcher at Uppsala University, and one from Carl Box, the CSO UK from Pion. So looking forward to having you again with us tomorrow. And with that, Jesus, I'm clicking to a lot of places. So with that, I want to thank you for being with us today, and see you tomorrow, same time. Bye.